Good morning, North Crowley. Today we're going to be talking about gas laws. We've already finished our chapter on gas laws, but I wanted to create a review for those of you who missed a few days during, the gas laws chapter. Mostly because gas laws are going to be about half of what our district assessment will be over in about 3 or 4 weeks. So today we're going to review that. I'm going to start by going over the concepts. We're going to go over the PowerPoint real quickly, and then I'm going to spend the rest of the time going over calculations. All right, so let's jump right into it. All right, so this is our combined gas law, and this is usually where we end up, but I like to start with it just to go over our variables. So first we have pressure, and as you can see, this side all says 1, and then this other side, everything here is a 2. So what we need to know is that 1 means initial. Initial, that means that's what we start with. So initial goes here, and then 2 is going to be our final. So this is P1, that means that's our initial pressure. So it's labeled down here. So P1 is our initial pressure, V1, that's our initial volume, T1 is our initial temperature, and N1 is not always included. Actually, the way we teach it, usually we just don't even include the number of moles, but it's here. It does belong in the total combined gas law, but sometimes you might see the combined gas law as just the 3 variables on both sides. So next I want to go over the units. So pressure could be seen in 3 different units. Actually, no, I was thinking volume. So volume can be in 3 different units. You need to input volume as liters. What you might often see is that volume is given to you in milliliters. So 1 liter is equal to 1,000 milliliters. And we're going to talk more about that later on. But if they give you milliliters, you have to convert to liters before you plug it into your equation. You could also be given centimeters cubed. So centimeters cubed is the same as milliliters. So if I say you have 500 centimeters cubed, that's the same as having 500 milliliters, which is the same as having 0.5 liters. We'll talk more about those conversions later on. But anytime you see liters, milliliters, or centimeters cubed, they're talking about volume. Temperature could come in 3 different units. Most likely you'll see 2 of them. You're either going to see Celsius or you're going to see Kelvin. Kelvin is what you need to input into the equation. If you put in Celsius, your answer is going to be wrong. So if they give you Celsius, you're going to have to convert to Kelvin. And the formula for that is Kelvin is equal to Celsius plus 273. Sometimes you're asked for an answer in Celsius. In that case, you're going to have to input your temperature as Kelvin, and then once you get an answer out as Kelvin, you have to convert to Celsius. And to do that, all you got to do, so Celsius is equal to Kelvin minus 273. So that's if they give you Celsius and they ask for a final answer in Celsius, you need to convert to Kelvin and then convert back to Celsius. So those are the temperature units, either Celsius or Kelvin. Liters, milliliters, centimeters, Celsius, and Kelvin. These are very simple, and a lot of you already know them and are able to identify them. Now, the new ones that usually confuse people are the units for pressure, and there are a total of 5. So here's them in order, or there's no real order. So we have ATM. ATM is atmosphere. We have PSI, which is the most commonly used in the U.S. for pumping, basketballs and volleyballs or whatever. We also have kPa. We also have mmHg, which is millimeters of mercury. And then we also have torr. So torr and millimeters of mercury are the same thing. So if you have 700 millimeters of mercury, you have 700 torr. But you need to know that either one of those units could be given to you, and you need to know that they're the same thing. The rest are a little bit different, but you just need to identify that anytime you see something that looks a little bit weird, it's probably pressure, because all of these you're very much familiar with. And lastly, we have N. N is going to be number of moles. So that's written right here, number of moles. If you have 3 moles, N is going to be 3. So that's basically it. Those are all of our units, and you need to know these units in order to do well on the calculations. So let's go ahead and move on. So now let's talk about pressure real quick. So this is the definition of pressure that you've probably seen in the past. Pressure is force divided by area. So the greater the force or the less the area, the higher the pressure. If you have a large area or a small force, you're going to have a lower pressure. In this case right here, the question was which of these is going to apply the greatest amount of pressure. So assuming the person who wears each of them is 100 pounds, so we're putting 100 pounds of force. So the area that's being pushed down on, the smaller the area, the greater the pressure. So in this case right here, you have a very large area. Here you have a very small area. So which one gives you the greatest force, or which one gives you the greatest pressure if you have the same amount of force? The answer to that is going to be the high heel shoes. So if we're assuming like 1 centimeter cubed, 1 cm cubed of area, where here you have 10 centimeters cubed, and then here you have 100 centimeters cubed. This one's going to apply a pressure of 1, this one's going to apply a pressure of 10, this one's going to apply a pressure of 100. So the greatest pressure is going to be this one because it's got the smallest area. Now this is the type of pressure that we're talking about. It's a little bit different than what we were talking about on the previous page. This pressure pertains directly to gas laws. So pressure depends on the number of molecules. And the way you want to think about that is the more molecules of gas you put in a basketball, the greater the pressure the basketball is going to have. So this is the key factor right here that affects pressure. So the more gas molecules present, the greater the pressure. Also the volume of the container. So if you have 2 basketballs, a regular basketball and a Dave & Buster's basketball, and you apply 10 pounds of pressure, so 10 psi, into each basketball, which one is going to have the greater pressure? We all know that if we put the same amount of gas in both of these basketballs, this one is going to have greater pressure because it's got a smaller container. So that's what they're talking about here. So if you have a larger container, you're going to have a smaller pressure. And we're going to talk about, or actually I can show you all right now. So let's pull this up. So here we have the simulation. We spent a good amount of time on this simulation. So if I pump in, well, let's have an exact number. So we're going to put in particles, and we're going to use a small container. So we'll put in 100 heavy particles, and 100 heavy particles give us 23.4 atmosphere. This is with a 5 nanometer volume, so our volume here is pretty small. And what's going to happen if we have the same number of particles but we double our volume? So we go from 5 all the way up to 10. So what do you think is going to happen to our pressure? So our pressure gets cut in half. So doubling the size of the container will cut your pressure in half. And well, we can add a little bit more volume. We can't double it, but we can add half to it. But the larger the container, the smaller the pressure. So let's jump back to this. So pressure also depends on the volume of the container. This is the second thing. And then thirdly, we have the average kinetic energy. So average kinetic energy, that's the definition of temperature. So temperature tells you how fast the molecules are moving, or the average of how fast the molecules are moving. If the molecules are moving at a fast rate, then your temperature is high. If the molecules are moving at a slow rate, then your temperature is low. And pressure depends on temperature. So as you increase the temperature of a container, we can go back to that container that we were just talking about. So over here. So our temperature right now is at 300 Kelvin. Let's cut our volume. Bring it back down to 10. If we increase the temperature of our container, what happens to our pressure? So first of all, our molecules are moving faster. Also, our pressure is increasing. And that's what you want to understand about pressure. So increasing the temperature will increase the rate that the gas molecules are moving. And as you increase the rate that the gas molecules move, you're also increasing the pressure. So average kinetic energy, that's the same thing as temperature. And if the temperature goes up, the pressure goes up. Lastly, and this one is very important because you're going to see a couple of questions on this. So collisions between the gas particles and the walls of the container exert a force on the wall. That force per unit is called gas pressure. So gas pressure is, so let's go back here, and I'm going to reset this. And what I want y'all to see is if I pump in gas and then pause it, we still have a pressure of 0. The reason we have a pressure of 0 is because the gas molecules haven't yet collided with the walls. And pressure isn't exerted until gas molecules hit the walls. And what I've been telling y'all in class is if we put a ball inside of this box with a pressure of 10 psi, and it's floating right in the middle, it's floating right here. What's the pressure on the box? Well, the box isn't going to have any pressure because the gas molecules aren't touching the walls. As soon as we allow the gas molecules to touch the walls, now we have a pressure. So if we go back here, what is this telling us? It's telling us that the gas molecules that touch the walls of the container, those are the gas molecules that exert a pressure. So if the gas molecules are not touching the walls, then there's no pressure. You're going to see that on the test. So if you already took the test, then you've already seen this type of question. Just know that the gas molecules colliding with the walls, those are the ones creating a pressure. All right, so again, these are the units of pressure. And the only thing I want to talk about here is STP. So STP is going to be standard temperature and pressure. And anytime you see STP, what you need to know is that they're talking about 0 degrees Celsius and 1 atm for your pressure. So if I tell you that you have, a volume of 10 at STP. What that means is that your volume is equal to 10, your pressure is equal to 1 atm, and then your temperature is equal to 0 degrees Celsius, but we need to input that. So 0 plus 273, which is 273. But that's basically what you want to understand about standard temperature and pressure. So sometimes they'll tell you that your pressure is at standard pressure, or they'll tell you that your temperature is at standard temperature. And sometimes they'll tell you that something else is at STP. So you just have to be able to read the question and know what they're telling you. Because STP gives you two different things. It gives you temperature and pressure. But sometimes a question will tell you that only your temperature is standard or only your pressure is standard, and you just need to identify what the question is saying. Over here, this is just a conversion. So 1 atm is equal to 101.3 kPa, and 0 degrees C is equal to 273 Kelvin. So you don't really need to memorize these. This is what you need to memorize. So 0 degrees C, 1 atm, that's standard temperature and pressure. And 0 degrees C you can easily convert to Kelvin just by adding 273. And anytime you're not given pressure, I would like for you to use ATM. Like, don't convert to kPa. There's no need for that. All right, we're not going to watch this. We don't need to talk about temperature today. All right, so pressure and temperature. At lower temperatures, gas molecules move slower, exert less pressure. We've already talked about that a little bit. Here they're pouring some liquid nitrogen over this inflated balloon. And as they're cooling the gas molecules inside the balloon, you can see that the pressure decreases and the volume decreases. At higher temperatures, gas molecules move faster and they exert a greater pressure. If y'all remember the demonstration we did in class where we heated the liquid and the gas inside of a cylinder and inflated a balloon. So as the temperature increased inside the container, you saw that the balloon inflated. All right, now we'll get into the gas laws. All right, so first we're going to talk about Boyle's law. And Boyle's law is P1 times V1 equals P2 times V2. It's not displayed how I like it, so I'm just going to rewrite it up here. So P1 times V1 equals P2 times V2. I don't like this right here, so I wouldn't write that. And basically what this one tells us is as your volume increases, so here our volume is doubling, what happens to our pressure? Our pressure decreases. This is the same as what we did in that simulation. So we can go back to the simulation. If we cut the volume in half, our pressure increases. We're at 3.7. If we double our volume, we're about doubling it here, our pressure decreases. That's Boyle's law right there. So as volume goes up, pressure goes down. As pressure goes up, well, really you don't want to think about it that way. So as volume goes up, pressure goes down. So this is the graph right here. So you can see pressure is over here on the side, volume is over here. So as volume goes up, so 1, 2, 3, all the way up to, we'll say 10 over here. As our volume goes up, our pressure continues to go down, and it's a gradual reduction. Like what I don't want you to do is on the test pick a line that goes straight, and that you'll see that that's an answer choice. But this is a gradual decrease, and this is the type of curve that you want to see when we're talking about Boyle's law. So let's move on to, let's talk a little bit more about it. So the volume and pressure of the gas are inversely related. What does that mean? It means as one increases, as pressure goes up, volume goes down. As volume goes up, pressure goes down. This is called an inverse relationship. This is another question that you might see on my test and the midterm. So just something to remember. And this is the only graph that looks different. So I always go over Boyle first because it is the one that looks different. You're going to see that the rest, they look more or less the same. So next we have Charles' law. And here's the Charles' law graph. And you can see that as temperature goes up, what happens to our volume? Our volume also goes up. So as temperature increases, we're going to put 0 over here, 10 over here, or we'll put 100 over here. It doesn't matter. As temperature increases, what happens to our volume? Our volume increases. This is called a direct relationship. As one goes up, the other goes up. As one goes down, the other goes down. So volume and absolute temperature of a gas are directly related. And a direct relationship shows us this kind of graph. So as one goes up, the other one goes up, and it's a straight line. And I also don't like the way the formula looks here, so I'll just rewrite it. So V1 over T1 equals V2 over T2. All right, next we have Gay-Lussac's law. And Gay-Lussac's law is a lot like Charles' law, and you'll see that when we solve these types of questions. So the pressure and temperature are directly related. So we'll put a 0 here and a 100 here. What happens to pressure as our temperature goes up? Well, pressure goes up. And this is also a direct relationship. As one increases, the other increases. And our formula should look like this. It's going to be P1 over T1 equals P2 over T2. Let's move on. All right, next we have Avogadro's principle, and this is one that we don't really talk about. We don't really solve very many with this, but this is where the n comes from in that combined that we talked about previously. And this is another example of a direct relationship. As the number of moles increases, the volume increases. And that's basically it. You're not going to solve very many of these, but it's just like Charles and Gay-Lussac. You solve them the exact same way. All right, lastly, we have the combined gas law, and the combined gas law is just a combination of all of them. So if we ignore the bottom, what law is this? This is going to be Boyle. If we ignore the pressure, this is going to be Charles. If we ignore the volume, this is going to be Gay-Lussac. And that's why it's the combined gas law. It's just a combination of all the gas laws in one. And this is where students struggle the most when it comes to solving equations, just because you're given so many variables. In most of the cases that we work out, you're only going to be given 5 variables, and you're going to have to solve for a 6th. Here it looks like 8, but I don't give you guys any with 8. It's always going to be 5, and you're going to solve for a 6th variable. All right, lastly we have, well, this is the last difficult one, but lastly we have PV equals nRT. And what's nice about PV equals nRT is everything here is either initial or final. Like you're not going to have to identify one or the other. So you only get one pressure, you only get one volume, you only get one number of moles. There's only one R constant, and then there's only one temperature. So you don't have to identify what's what. Everything you're given is just going to plug right into your equation. Students get confused here because they forget what the R constant is. You're given the R constant, it's written on the board. You just got to know that if it's an ideal gas problem, you need to plug in an R. And I find them pretty simple to identify because you're only given one of each variable. If it says moles anywhere in the equation, then it's an ideal gas because moles are only an ideal gas. They're also in Avogadro's principle, but like I said, we're not going to be working any of those. So anytime you see moles, you know that that's an ideal gas law equation. Now here are our ideal gas constants. If you're given ATM, then you're going to be using this constant right here. If you're given kPa, you're going to be using this constant right here. And that's about it. You don't need to memorize the values. They're both provided to you and they're labeled, so kPa and ATM. You just need to know which one to use in which equation. And we'll solve a couple in a little bit just so you're able to do that on your own. All right, so Dalton's principle, it's very unlikely that you'll ever see a question like this again because I didn't even include these on the test. They're just too simple. So basically your total pressure is, it's equal to all the pressures combined. So in this case right here, we have a bunch of pressures, different gases, but as we know that all gases exert the same amount of pressure depending on the volume of that gas. So here we have different pressures of gas. If we wanted to know the combined pressure, all we do is add them up. Another type of problem that you could see in the future for Dalton's law is you could be given the total pressure and asked to calculate the pressure of one of the things inside the container. Well, in that case, all you have to do is add and then subtract, and then the remainder is going to be the pressure of the unknown that you're solving for. You're not going to be solving any of these, so I'm not going to spend any time on these. All right, so that's it. Those are the gas law notes. And I'm going to post this video on its own, and then the calculations are going to be their own video. And I'll see you guys in the next one.